Hello. Welcome back to class. Our last class of the week. Let me know who's here. I see there's only a few of you at this point, but hopefully a couple more people trickle in before class starts. Navik on time as usual. Good morning. Good morning, Taylor. Any issues with the quiz this morning, or did the uploads and everything work smoothly? It went good. All right, nice. Yeah, that first day when I gave you the wrong quiz, that was a disaster. But I think we're starting to get used to the technology. We'll get started in about a minute or so. See, people are still trickling in. Happy Friday, Emma. But really, like, at this point, are the days even different? I know we don't have class tomorrow, but every day is the same right now, it feels like. Good morning, Liza. Good morning, Shitong. All right, well, it's 9 o'clock. We could get started. So if anybody has their coffee or water or tea ready, they could join in on the simultaneous sip. That might have been the best one this week. I don't know. Okay, so the plan for today is we're going to just continue 6.5. Good morning, Patrick. We're going to continue 6.5. We'll probably finish it. It's going to be mostly examples again today. Sister sip, excellent. Emma, I was getting worried if your sister gave up on joining us for the simultaneous sip, but it seems like she's back and joining us. Yeah, so it's going to be, we'll start with a theorem and then we'll get a few examples going. Okay, so we saw at the end of class yesterday, we saw two examples during class yesterday. One example had one of these least square problems had a unique solution. One of them had infinitely many solutions. So our theorem is going to tell us when are we in which case. So the theorem says let A be an m by n matrix. The following are equivalent. First, the equation ax equals b has a unique least squares solution for all B. Next, the columns of A, the columns of our matrix, are linearly independent. Okay, so if we could just check that the columns of our matrix are linearly independent, we automatically know that AX equals B has a unique least squares solution. And then last, the matrix A transpose A is invertible. Okay, and so when these are all true, right? So what this theorem says is these are either all true or all false. The easiest one for us to check is B, checking if the columns are linearly independent. So if we just check that the columns are linearly independent, we automatically know there's a unique least squares solution and that A transpose A is invertible. And more important, when these are all true, the least squares solution, which we called x hat, is given by x hat equals A transpose A inverse. So we got to find the inverse of this matrix times the vector A transpose A. A transpose B. Okay, so this gives us a way. This gives us a way of finding x hat, without having to do row reduction or anything. All right, so let's take a look at an example. So we'll find the least squares solution of AX equals B. A is the matrix -1, 2, -1, 2, -3, 3. And B is the vector 4, 1, 2. Okay, so you should confirm that the columns of A are linearly independent. And then we're allowed to use this theorem. And so the theorem tells us how we would find the solution. Okay, so I'll give you, let's say, a minute and a half or so to work this out. Ask any questions you may have in the chat, but then we can work it through together. All right. I don't expect you to finish the question in that amount of time, but yeah, like I've said 1,000 times since we've moved to online, it's hard for me to tell, if people know what they're doing or not, just because, I can't see any of you. All right, so we want to first show that the columns are linearly independent. How do we know that the columns are linearly independent? Okay, well, I'll answer it. We know the columns of A are linearly independent since there's only two of them and they're not scalar multiples of each other. So since A has two columns and they are not scalar multiples of each other, the columns of A are linearly independent. Okay, so we're allowed to use this theorem. So we need to find A transpose A, then the inverse of that matrix, and then A transpose B, and then we'll take their product. Okay? So A transpose A is this product, which we could work out to be 6 minus 2 minus 6 minus 3 is minus 11. Minus 11. And 4 plus 9 plus 9 is 22. Okay, so that's A transpose A. We need the inverse. We need the inverse of this matrix. So how do we find the inverse of a 2 by 2 matrix? Well, we need a determinant. The determinant of A transpose A is 6 times 22, which is 132, minus 121, which is 11. So A transpose A inverse is 1 over 11 times the matrix where you switch the main diagonal and you change the sign of the other diagonal. Okay, and now we just need A transpose B. Okay, so we do this multiplication out. We get minus 4 and 8 plus 6 minus 3 is 11. Okay, and so now we're basically done, right? We know x hat is equal to this matrix times this vector. So this works out to be 33 over 22, which is the vector 3, 2. Okay, so the solution, what does this say? It's saying if we took A and multiplied it to the vector 3, 2, we'd get as close as possible to B. Shouldn't the ATA inverse matrix have a 4 in the bottom left? This one? So to get the inverse of this matrix, you switch these entries, and then you switch these two to negatives. Am I missing? Are you talking about this matrix? Maybe you couldn't read my handwriting here? This is an 11, negative 11 here. Yeah, my bad. That definitely looked like a negative 4. Yeah, my bad. Yeah, so that was a negative 11. And then, so your calculation probably is going to end up being a little bit different, but the steps are the same. Okay. Yeah, so this theorem was helpful. It speeds it up. And another nice thing is, like, so these types of questions, we're not going to get into any of the applications, unfortunately, but solving these types of questions have a lot of applications in computer science. And this is pretty easy to program. Okay. So another thing of interest is we know that A times 3, 2 gives us as close to B as possible, but we could ask, how close are we? So when a least squares solution X is used to produce AX as an approximation of B, the distance from B to AX is called the least squares error. Of the approximation. Okay, so let's take a look at an example of finding the least squares error. So we're going to look at the matrix and the vector that we did examples with yesterday. All right, so given that A is the matrix 4, 0, 1, 0, 2, 1, and B is the vector 2, 0, 11. So this is the matrix and vector we looked at yesterday. Determine the least squares error. In the least squares solution of AX equals B. Okay, and just recall, you could look back in your notes yesterday, that we found X to be the vector 1, 2. Okay, so we found yesterday that 1, 2 was the solution of the least squares problem. So using this, let's find the least squares error. So does somebody want to say in the chat how they're going to find this least squares error? Find the length of B minus AX. Yeah, exactly. So we should find A times X, and then take the difference, and then find the magnitude. Right, because the length of B minus AX is the same thing as the distance from B to AX. Oh, sorry, this is a typo I had. This should be AX with the hat. So we're going to use our solution here. So AX is the matrix 4, 0, 1, 0, 2, 1 times the vector 1, 2. Which is 4, 4, 3. The vector B minus AX is minus 2, minus 4, 8, and its length is the square root of the sum of the squares. The fact that we're dealing with the sum of squares also is why it's called the least squares. As you go into different branches of math, the concept of length gets generalized, and you don't have to use like the Pythagorean length that we see in geometry. You could use other what are called norms. So this is the one that has squares. So it's the least squares error. So the least squares error here. So the closest, I guess the column space of A is to the vector B is the square root of 84. So B is the square root of 84 away from the column space of A, is what this says. Can I get some thumbs up in the chat if we're good with this question? Or ask any questions you may have if you have a question. All right, we got a few thumbs up. That's good. Yesterday in my calc class, I asked the same thing. You know, give me a thumbs up if we're good to go on, and it's just silence, except for one person writes, the chat's broken. How do they type it? How do they write the chat's broken if the chat is broken? So, drives you nuts. Okay. So we're going to look at a special case now. It's how do we solve these types of problems when the columns of our matrix are orthogonal? So when the columns of A are orthogonal, which is not the case that we just looked at, right? If we took their dot products, we would get 1, which is not means they're not orthogonal. So when the columns of A are orthogonal, we could use orthogonal projection to find the least squares solution. Of AX equals B. So what we're going to solve we will solve AX equals the projection onto the column space of A of B. Okay, so let's take a look at an example. So find the least squares solution of AX equals B. Where A is the matrix (1, 1, 1, 1), -6, -2, 1, 7. And B is the vector -1, 2, 1, 6. Okay, and we'll solve it using this method here. So what I want you to do is first show that the columns of A are orthogonal. Okay, so can somebody tell us in the chat, how do we show that the columns of A are orthogonal? So I'll write this down. So we want to show columns of A are orthogonal, and then find the projection onto the column space of A of B. And then we'll solve the equation AX equals this matrix. Yep, exactly, Taylor. So yeah, the way we show columns are orthogonal is we just take the dot product and show that it's 0. And then we want to project B onto the column space of A. So that's the same thing as projecting B onto the subspace that's spanned by the columns of A. Now, so it'd be like A1.B over A1.A1 times A1 plus A2.B over A2.A2 times A2. All right, I'm going to start working it out now just so we have time to wrap up before the 9 o'clock students take their quiz. So let's just take the dot product. A1.A2 is equal to 1 times -6 plus 1 times -2 plus 1 times 1 plus 1 times 7. -8 plus 8 is 0. So our matrix has orthogonal columns. The projection, we'll call this B hat just for the sake of space. The projection onto the column space of A is B dot A1 over A1 dot A1 times A1 plus B dot A2 over A2 dot A2 times A2. So B dot A1 is -1 plus 2 plus 1 plus 6. So that's 8. A1 dotted with itself is 1 plus 1 plus 1 plus 1, which is 4. B dot A2 is 6 minus 4 plus 1 plus 42, which is 45. And A2 dotted with itself is 36 plus 4 which is 40, plus 1 plus 49, which is 50. 40 plus 50 is 90. Okay, so now we can add these vectors together. And we get, well, we get this. It doesn't really matter what these add up to. All right, let's see if we could explain why. This equation, all right, let me simplify it a bit, just so we don't have fractions. B. This is saying that A is a matrix, A times the vector 2, 1/2 gives us B. This is the solution. These are the weights of the columns that give us B. That's exactly what we're looking for. So we don't even have to write out what B is. We can just read off the weights right there. So X equals 2, 1/2. So in general, if A has columns that are orthogonal, this dot product over, so B dot A1 over A1 dot A1, that gives us the first entry of our least squares solution. B dot A2 over A2 dot A2 gives us the second entry. And you can imagine if there's more columns, you could continue this and get the next entries. Right? You could have gone through and figured out what B is and then solved AX equals B using row reduction. And you would get this answer. But why do that when we already have it written out? So are there any questions on this or any of the examples we've done so far today? Navik, that's a great point. He says, don't forget to hit the like button. Well, if there's no questions, the 9 o'clock students have to take the quiz in 3 minutes. So we could stop here. Yeah, so just, I guess I'll say what I try to say at the end of each week. Be safe this weekend. Stay inside. I don't know. You know the drill at this point. Wear a mask if you must go outside. All those kind of things. I'll stay around and answer any questions you may have. But yeah, so next week's our last full week. Can you believe it? Navik loves my shirt. Thank you. Our last full week of class. Is that sad or is that happy? I don't know. Okay, remember, hit the like button before you get out of here. It's so important. We are so close. It is sad, Emma. We are so close to 1,000 subscribers. Only 300 away. It's not bad. No problem, Echo. Glad you made it to class. But yeah, if there's no more questions, I'm going to end the stream. So have a good weekend. Shoot me an email if you want to chat about anything. I'm happy to Zoom. Bye-bye.